Thank you, Danielle, and good afternoon to everyone. Today we'll talk about stratigraphic hierarchy, and it's a segue into the next main segment of the series of lectures. We're getting into seismic stratigraphy and sequence stratigraphy. These are topics that I know generate a lot of interest among students and faculty and other industry workers. So that hierarchy is shown here. I'll get into the details as we progress, but we start from very thin, limited extent units like lamina. Several lamina build a lamina set, which builds beds, and all the way down to sequence sets, which are very thick units, very widespread, and encompass a lot of geological time. This is my slide about terms of use. Essentially, the materials, both the archive videos and the lecture PowerPoints and the exercises are intended for use by students or faculty that teach students. It's not to be used for people who are already working, especially in the oil and gas industry. So the fundamentals of stratigraphy come from our study of modern deposits and also from sedimentary outcrops. So a couple of pictures here. The upper left, modern deposits. There's a glacier back here. I believe the photo is from somewhere in Alaska, and the meltwater is coming out and it's carrying some sediment with it. It's building a little fan delta here at the head of the inlet. And you see the greenish color, that's water with a lot of sediment outwashed from the glacier. These are classic outcrops in Ireland on the upper right. These are the Cliffs of Moher. These are deep water turbidite deposits. And then the lower image is of the Grand Canyon. Probably half of you at least have been to the Grand Canyon. Hopefully all of you have read a little bit about the stratigraphy in the Grand Canyon. And then on the far right is an example of a measured section, how sedimentologists and stratigraphers capture information from outcrops and convey that to other people in their field. So we can get stratigraphy from well data. So we've drilled a hole, and we can get cores, and there's a photo of two segments of a core on the far left. We can also get well logs, some sort of a measurement of the rocks or the rock properties. We can also get fluid properties. We can get things like temperatures and pressures. And then we can get information from several wells. So I have a 3-well cross-section, well A, well B, and well C. And some correlations have been done here, and some colors have been applied. The gray would be shales, the yellows would be sands, and the reddish-orange would be fluvial deposits. This is a cross-section from a publication by John Van Wagner and some of his co-authors. We can also get stratigraphy from seismic data. And so this is a seismic line that we'll be using later on in the course for one of the exercises. And the darker black lines with the numbers on them are interpreted major boundaries. And we can do some interpretation here as to what sorts of environments of deposition we have. So the brown is delta plain, the yellow is delta front, the light green is delta slope, the darker green would be basinal shales, and then the orange units are deep water fan units that could have reservoir quality sand within it. And this happens to be an area that I worked way back in 1980 when we had no well control out here. And so all of the stratigraphy that was interpreted, predicted, was based only on seismic data. With our stratigraphic analysis, we're going to make observations using the stratigraphic data, and we're going to turn that into predictions about the stratigraphy And one of the methods by which we can make those predictions is that we'll use depositional models that we have available. So as an example, the upper left is meant to be a map view. The pink colored blobs are salt walls. There's a little gap in between two salt walls here. Sediment filled a shallower mini basin up here, and when that was filled to the spill point of this little fairway, sediment started to infill the next deeper mini basin. And with 3D seismic data, we can actually see things like these distributary channels that are marked on these different deep water fan lobes. So if we make our observations and we come up with an interpretation in a map view like this, we can make use of a depositional model for what happens at the base of a slope as sediments come down a canyon and then start to, the turbidity currents start to slow down as the gradient decreases. And we start to get, we start with confined flow on the slope in the canyons. We go into semi-confined flow and then unconfined flow. And that's based on a depositional model that is based on a lot of outcrop studies and flume experiments and other data. And then if I am in the upper portion of this map, it's reminiscent of this portion of the depositional model. And so I can make a prediction as to how the reservoir quality sands, which is the light yellow, might be distributed laterally and also vertically, how they stack. If I am further out in the more distal part of these fans, I would be in this part of the depositional model. And so then I might predict this type of distribution of sands. So a caution about seismic data, the resolution on seismic is much less than most stratigraphers, especially those that work outcrops, are used to. The units that we deal with doing seismic analysis are often tens of meters to hundreds of meters thick. So the image of the seismic is a very old piece of seismic, which allowed me to get it released. And an old trick that I learned was use a red pencil and try to connect up some of the black peaks and help the data processors get more reflector continuity. And so the scale bar on the right shows 500 meters. So one of these white and yellow blocks are 100 meters. So if I look at this red in this peak and this red in this peak, that interval from peak to peak or red line to red line is on the order of 100 meters. So the scale of stratigraphic correlation changes depending on what type of data set we have. If we're working with outcrops or we have cores or this photo is taken from a trench that was dug in the beach on Galveston Island, we can do a very fine scale correlation of very small units. We can see individual lamina. The lamina would be the lighter and darker bands in this photo. The units are a couple of centimeters to maybe a meter thick. If we're using well log data, our resolution is less. We're looking at units that might be a couple of meters thick. We use pattern correlation of the different log markers. And again, I have 3 wells here, and they have been correlated and then color-coded based on environment of deposition, which is from which we can infer lithologies. If we're looking at seismic data, we're able to correlate on units that are called parasequences, and I'll define what that is as we proceed today. These are much larger units, tens of meters to hundreds of meters thick. And so here's a piece of seismic, and I have an orange and a lavender and an aqua and a light green package of rocks. And you can see the scale 0 to 300 meters. So depending on whether we're working with seismic or logs or cores and outcrops, we go from low resolution with the seismic to medium resolution with well log correlation to high resolution if we have outcrop or core or modern deposits. However, our outcrops usually are limited in lateral extent, and maybe we only see one orientation on our outcrop. With well logs, we get more aerial extent, however far those wells are separated from each other. If we have, say, 20 wells in a field, and the field might be 20 kilometers by 12 kilometers, that has a bigger extent than most outcrops. With seismic, its big strength is that we can get extremely large aerial extent. And so as an example, if you're working the U.S. Gulf Coast, we have seismic coverage for the entire U.S. shelf and slope. Much of that coverage is 3D seismic these days, although there are some areas where we may only have dense 2D seismic. So the strengths of seismic data, as I mentioned, good aerial coverage. We're able to image major depositional units. We're able to identify potential source intervals and reservoir intervals and sealing units. And we can build a stratigraphic framework, and with that seismic data, we can incorporate stratigraphic information from well data. We can model how the basin filled through geological time, get a basin fill history, and then we can look at the hydrocarbon systems, source reservoir, trap seal, and migration. The weaknesses of seismic data in terms of doing stratigraphic analysis, we have limited vertical and lateral resolution such that we can't see real small features. But typically in the oil and gas industry, we're not interested in extremely small features. We're interested in features that will hold enough oil or gas that we can turn a profit. The stratigraphic interpretation is limited by the quality of the seismic data or the seismic imaging. So the better image to the subsurface is, the more accurate my stratigraphic predictions will be. Seismic responses are non-unique. So I may have an area on the seismic where I have very low amplitude reflections. So low amplitude means that the velocities and densities are not varying too much to give me high valued reflection coefficients. So that tends to be areas where we have a fairly homogeneous lithology. So we might have a mass of sand, or we might have a thick shale, or we might have a salt diapir. So low amplitude by itself, without looking at a context in terms of the basin development and the lateral associations, doesn't give me that much information. In new areas, meaning areas that we may not have too many wells, we may have to jump correlate from an adjacent outcrop into the area that we're studying, or we may have to go from one mini basin in the Gulf of Mexico, for example, to the next mini basin deeper down dip. We can also have post-depositional erosion or structuring, and that can hamper our ability to properly correlate stratigraphic units and figure out what sorts of environments of deposition and lithologies we're dealing with. And typically we can't see the hydrocarbons directly. We can just look for the proper conditions where we think we have source reservoir, trap, seal, and migration. So our methodology, we're going to make stratigraphic observations. We can use modern examples, current depositional bodies. We can look at ancient bodies, outcrop. We can look at things like a flume and model different processes, such as a turbidity flow, which is shown here in this image. And then we do have, especially in the energy industry, a wealth of previously drilled wells that has seismic associated with it. And so we can learn things by making seismic-based predictions, drilling wells, and seeing what we predicted correctly and what we did not. We will take those general observations and we'll develop a series of conceptual models. So this is one example. This is for mass transport complexes. This is where we have some failure on a continental slope and some slumping and sliding. And so by studying modern examples and outcrops and processes and doing extracting learnings from where we've actually drilled and encountered these types of deposits, we can build a conceptual model. And those models, there's various models published through academia. Oil companies have models that they've published, and then most companies also have models that are still considered confidential and not available to people outside of the individual companies. We also have local data from the area that we're examining, prospecting in perhaps. Maybe we have some wells. Some of those wells may have cores. Most wells would have well log data. And then in the area that we're studying, we should always have some seismic data. It might be 2D, it might be regional 2D, it might be dense 2D, or we might have good quality 3D seismic. And so we'll take our local data, we'll interpret that, making use of our conceptual models, and then we'll make predictions as to things such as depositional environments. So in this map view, the brown is fluvial and delta plain. The slide has an error. This should be delta front instead of delta plain, and then delta slope in the green. And this is this piece of seismic, and this map was published by George Ramsayer back in 1979. So there is a hierarchy of stratal units or stratal packages that extend from local thin lamina that form in a matter of minutes or weeks or a month to thick regional depositional sequences and sequence sets that might be on the order of 3 to 10 million years of depositional time. So this is what I showed on the first slide. Thin units, limited extent, going up to deep to bigger and bigger, more widespread, more geological time units. And so a series of lamina will build lamina sets. Several related lamina sets will build a bed. Several beds will form a bed set. Bed sets build together to form a parasequence. Several parasequences will build a parasequence set. Several parasequence sets build sequences, and sequences build sequence sets. So what we're able to look at depends on the tools that we're using. If we're using core or outcrop, we can see the very fine scale stratigraphy, lamina, lamina sets, beds, maybe bed sets. If we're looking at logs, unless we have a log that has a camera associated with it, an image log, we can't see the lamina sets, but we can interpret the beds, bed sets, parasequences, parasequence sets. With seismic data, again, we can't see the very small and even some of the mid-size stratal units or packages, but we can see parasequences, parasequence sets, sequences, and sequence sets. So when we're talking about using seismic to try to get stratigraphy, we're looking at the higher end of the stratigraphic hierarchy, the parasequences, parasequence sets, sequences, and perhaps even sequence sets. So these hierarchical units have two fundamental properties. Each stratal unit, with the exception of lamina, is a genetically related succession of strata, and they are bounded by chronostratigraphically significant surfaces or time significant surfaces. And then each surface, these time significant chronostratigraphic surfaces is a single physical boundary, and everywhere this boundary separates strata above from strata below. And in most cases, the older strata will be below the surface, younger strata would be above. The only exception is if we're in a structural regime where we've had compression, we can get the original depositional units flipped over, overturned. And so in those cases, current day, we might see younger units sitting below older units. But at the time of deposition, we would always have older lower. So here's a photo of an outcrop. The purple arrows are meant to represent bed sets. We have an individual bed, and the green would be individual beds. And if we zoom in on this portion, we can see the light and dark color lamina and lamina sets, and those, so lamina build the lamina sets, several lamina sets build the beds in green, several beds build the bed sets. So we have one bed set, a second bed set, a third bed set, and a fourth bed set. This is the photo I showed earlier. This is from Galveston Island, where some new hires with shovels dug a trench in the sand of the beach, and then the experienced instructor takes a machete and tries to get a clean cut face. And so in bed 5, you can see the darker and lighter bands. Those would be individual laminas. Several related lamina would build a lamina set, so there might be 1, 2, 3, maybe 4 lamina sets. And the red lines are the boundaries between bed 1, bed 2, bed 3, bed 4, bed 5, bed 6. So those are also referred to as bedding surfaces. And those bedding surfaces, the red lines, mark a break or a change in deposition. So here's an outcrop. This is from West Texas, 2 people for scale. So at the base of the outcrop is bed set 1. We have a more significant break in deposition, a bed set boundary in purple. We have bed set number 2, another more significant boundary marked with purple. And if I zoom out, we can see that there's 1, 2, 3, 4, 5 bed sets that have been identified. There's probably 6, 7, and 8 up higher on the outcrop face. But you can see how these units build one on top of the other. Bed sets stack to form parasequences. And this measured section diagram shows a typical parasequence in a marginal marine setting. The boundaries for parasequences are flooding surfaces. So we have a flooding surface marked in red at the base, another flooding surface towards the top. And we go from a relatively deeper water setting. As we move through the parasequence, we get into shallower and shallower water conditions. Or a term that is commonly used is we say we have a shoaling upward sequence. So we go from an offshore environment to a lower shore face, to an upper shore face, to a foreshore. Then we have another flooding event, and we go back into some offshore depositional environment. If we had a gamma ray log, this might be the response to that. The gamma ray measures the natural radioactivity. The shalier units are more highly radioactive, so they plot further to the right. The sands, less radioactive material, so they're lower values, and to the left. So we have a step left to right, and then we see the response is slowly drifting towards the left on the log. We have another deepening flooding event, the top of a parasequence, more radioactivity as we have more shale, and that would start another cycle where we would shoal upward, go from relatively deeper to shallower water, have less and less radioactive material, and so the gamma ray response would go from high values near the just above the flooding surface to lower values as we get to the top of a particular parasequence. The parasequence is the basic unit of cyclic deposition. So here's the definition for a parasequence. It's a relatively conformable succession of genetically related beds and bed sets bounded by marine flooding surfaces or their correlative surfaces. The characteristics, if we're in a marginal marine setting, is that we'll see a shoaling upward sequence. And so you could also say that the relative water depth is decreasing. We see grain size increasing upward from shales to silts to sands. The parasequence boundaries or flooding surfaces represent surfaces above which there's an abrupt shift to a deeper water facies. And parasequence boundaries approximate geological timelines, and that thus they can be used to create a high-resolution sequence stratigraphic framework. So here is an outcrop. I believe this is from Utah. We start at the base in pro-delta, relatively deep water. We go into delta front to stream mouth bar to delta plain, and then we have a parasequence boundary, the dotted green line, and we're back into a delta front, so a deeper water setting than the delta plain. So this dotted green line would be a minor flooding event, and there's an abrupt shift in the depositional facies or depositional environments from shallower to deeper across that dotted green line. Several parasequences that are related will stack and form what's called a parasequence set. And so again, for a marginal marine parasequence, we might have in green coastal plain sands and muds. The yellow would be shallow marine sandstones, and the grays would be shelfal mudstones. So we have one episode or pulse of deposition leading to parasequence number one. We have a minor flooding event. We have a second pulse, a minor flooding event, a third pulse, a minor flooding event, and a fourth pulse. And so we have 4 parasequences stacking to form a parasequence set. In this case, as you go from 1 to 2 to 3 to 4, all of the facies bands are moving from left to right or up dip to down dip. And so overall, sedimentation is outpacing the space that we have, the accommodation we have for sediments. And so our shoreline and all our other stratigraphic units would be migrating basinward. So that's, this slide has the same image that was on the previous one. If sediment supplies outpaces accommodation, we'll get a migration of the shoreline and the beach and all the other facies basinward. And so we call this a progradational stacking pattern. In the red box, if I had a log there, the self-potential SP would have this type of a response. The gamma ray would have this type of a response. Now we can also have a condition where we create more space than the sediment is able to keep track of. And so for parasequence 1, we backstep for 2, we backstep for 3, we backstep for 4. So this is a retrogradational stacking pattern. Some other terms that people use is they call this a transgression, and they call this a regression. So we have a transgressive cycle and we have a regressive cycle. And we could have the case where there's pretty much of a balance between accommodation space and sediment supply. And so the shoreline and all the facies bands stack fairly vertically. And so as we go from 1 to 2 to 3 to 4, we see the yellow shallow marine sandstones are staying about in the same position as opposed to backstepping, moving towards the continent, or stepping out, building out towards the basin in a progradational pattern. So we'll look at our parasequences and how several of them stack and decide if we're in a progradational stacking pattern, a retrogradational stacking pattern, or an aggradational stacking pattern. Going up the hierarchy to the next step, that's the depositional sequence. And a depositional sequence is a relatively conformable succession of genetically related strata, bounded at its top and base by unconformities or their correlative conformities. And when you see 1977 as the year for a reference, that would be AAPG Memoir 26, which is the foundational textbook for seismic stratigraphy that then evolved into sequence stratigraphy, or I guess evolved is okay. Characteristic of a depositional sequence, parasequences and parasequence sets are the building blocks of depositional sequences, and the depositional sequence is the fundamental stratal unit for sequence stratigraphic analysis. Bob Mitchum, 1977. So again, this is referring back to AAPG Memoir 26. And then a seismic sequence is very simply a depositional sequence that we identify using seismic data, so on seismic sections or in seismic 3D volumes. This is an example from the Book Cliffs in Utah, the Black Hawk and Castlegate formations. And so some of the environments are shown. The inverted triangles, gray with PS, this would be a parasequence 1, parasequence 2, another parasequence, another parasequence, another parasequence. And then on the far left, these inverted yellow triangles, this would be a parasequence set, a second one, a third one, and a fourth one. So again, we can look at outcrops, we can look at cores, we can interpret well logs, or we can interpret seismic data, and we can look for this hierarchy of stratal units. So there are two exercises associated with lecture 20. I'll talk a little bit about 20A just to give you a feel for what it is. We have 5 wells, A, B, C, D, and E. We have an SP log that's self-potential. And the task is to take these logs and break them into parasequences and parasequence sets. And so the SP is a measure of electrical differential between the surface and where the tool is in the subsurface. And similar to the gamma ray, we see a drift of the response of the SP right to left as we're in a shoaling upward parasequence. And then when we have a flooding event, we see a sharp shift to the right and drift to the left, shift to the right, drift to the left. And so that's the basic information you need to do the exercise. So we can look at any of the wells, and as you go through the text, it will walk you through this. But the first step is to look for these shoaling upward, and a few of them are marked. So here's one parasequence, here's a second one, here's a third one, here's a fourth one. And there's a major flooding surface here as we go from the stippled shallow marine into shelfal mudstones. And so we have some marked in well E and one that's marked in well C. So if you do the exercise, you would do the same type of analysis for the entire length of the shown well A, B, C, D, and E. The first step would be to look at each well individually and see if you can see some of the parasequence boundaries where we have flooding, and then look for some of the more significant boundaries. Another major flooding event, we go from coastal plain below to shelfal mudstones. So right in this region here would be a parasequence set boundary. Oh, it looks like the same sort of signature over here. And so without giving away all the work, I'll leave you with that. So that concludes my prepared statements. And I'll put this slide up, show you where we've been in our series and where we hope to go next. Thursday of this week, I'll be talking about seismic sequences. So I'll turn it back to Dr. Sumi to see if there are some questions that the audience has typed into their message box.
Great, thank you, Fred. We do have one question from Isabel. She asks, how far can I go with carbonates? Is it possible to build a good stratigraphic hierarchy model with seismic profiles?
Yes, we can use the same techniques that I'll be talking about on Thursday in clastic basins and also in carbonate basins. And there are some interesting differences between carbonates and clastics. I don't really have in this series a lecture to talk about carbonate depositional environments. There is some papers in the AAPG Memoir 26 about carbonates. And then there's a publication, I think Rick Sarg is one of the editors, that talks about carbonate seismic sequence stratigraphy. So yes, we can do the same type of stratigraphic interpretation with carbonates as we can with clastics.
Great, thank you. Patrick asks, what do you do first in a frontier area, drill or seismic?
Oh, we would never drill without doing seismic analysis. And so the seismic is much cheaper and gives you more aerial extent of information than a well. And I can't think of any case, except maybe in some unconventional plays, where they would drill without first having seismic data acquired, processed, and interpreted. So I would say the first 15 years of my industry experience was working in basins with no well control or very limited well control, and almost all of the predictions that were used to locate an exploration well and then drill it was derived from seismic data.
Great, thank you. So those were the only two questions that we received today. So thank you so much, Fred. Oh wait, we got one more coming in. John asks, is there a particular association or link of any of the parasequence types to having good HC play?
There are. There's an AAPG study series, and I can't remember the name of it. John Van Wagner is the first author of that, and it talks about sequence stratigraphy, and then it talks about where in the Exxon model of sequence development would you have different types of hydrocarbon play possibilities. And so I will talk a little bit about that later on, maybe on the seismic facies, September 14. And if I can get your email address, I'll get that from Danielle. I'll look up that reference and send it to you.
Great, thank you, Fred. And yeah, so I think that completes our webinar for today. Thank you so much for the presentation. And I will, please join us on September 7th for our webinar on seismic sequences. And I also put in the chat box about how you can sign up for the IRIS Message Center, so you will always get the updates of when the next webinar is and what it'll be on. All right, well, everyone have a good rest of your day, and talk with you all soon. All right, see you, Fred. Thanks.
Hey, thank you very much, and everyone have a great day.
All right, great.
Bye-bye.
Bye.